Hello everyone, can you hear me?
Yes, we can hear you.
Okay. Arif,
Yes,
ใส่หูฟังหน่อย
yes, I can hear you.
Today we have three group for presentation. The first group is Ramzan and Arif. The second is Adamu and Asuka, and the last group is Salihu and Sani. For the first group, if you're ready, you can start.
Ramzan, please open the mic.
Yes, can I share the screen?
Yeah, you can share your screen.
Can you see my screen?
Yeah, I see.
Hello, everyone. I am Muhammad Ramzan, and my group fellow is Mr. Muhammad Arif. Today, we are going to present the topic MHD flow of micropolar and Williamson fluids over a bidirectional stretching surface. The layout of the presentations are: first, we will discuss introduction, research methodology, problem statement, significance of the research, literature review, and problem formulations. At the end, we will discuss some proposed work related to the present work. In introduction sections, first we will discuss the fluid and their types. Fluid, a material that has no fixed shape and deforms under an applied stress, is known as a fluids. Fluid can be further divided into two categories, such as first one is the Newtonian fluids and second one is the non-Newtonian fluids. In Newtonian fluids, those fluids which obeys Newton's law of viscosity is known as Newtonian fluid. And those fluid which does not obey Newton's law of viscosity is known as non-Newtonian fluids. These are some examples of the non-Newtonian fluids. Non-Newtonian fluids are further divided into three categories, such as rate type fluids, integral type fluids, differential type fluids. The fluid in which the deformation rate dt is proportional to the stress is known as rate type fluid. The fluids in which the response functions can be represented as the integral polynomial is known as integral type fluids. The last one is the differential type fluids, in which the stress depends only a finite number of derivatives. Heat transfer. Heat transfer is the process of transfer of heat from a high temperature system to a low temperature systems. The applications of heat transfer are solar collectors, cooling chambers, and lubricants. Mechanism of heat transfers. These are three methods in which the heat can be transferred. First one is the conductions, second one is the convections, and third one is the radiations. From this figure, the method of heat transfer can be explained more clearly if we see that this is the conductions here, by the contact of the body, the heat can be transferred is known as the conductions. But in radiations, the heat can be transferred through an electromagnetic waves. And this process is known as the convections. Now, next one is the magnetohydrodynamics. Magnetohydrodynamic is the study of magnetic properties and behavior of electrically conducting fluids. It is also known as MHD. It was initiated by Hannes Alfons. He received the Nobel Prize in Physics 1917. The applications of magnetic field are magnetotropy, MRI, and magnetic hypothermia. These are the paper. On the basis of these paper, we try to model our problems. Now, research methodology. First, we proposed a problem which consists of a mathematical formulations, and mathematical formulation which consists of initial conditions and governing equations along with initial conditions and boundary conditions. In governing equations, we have three equations like velocity equations, energy equations, and concentration equations. These are partial differential equations and in a non-dimensional form. Then we have some similarity variables. After applying these similarity variables on the partial differential equations, these partial differential equations can be converted into ordinary differential equations in a dimensionless form. After this, the Ham method, homotopy analysis method, is employed to find out the solution of temperature field, velocity field, and concentration field in a graphical form. Formulation of the problem. These are some flow assumptions that we will discuss in our model. The fluid is steady and incompressible. Micropolar, we are going to study the micropolar and Williamson fluid, which is three-dimensional. Also, we can check the effect of applied magnetic field, mixed convection effect, thermal radiations and chemical reaction effects, Brownian motion, and thermophoresis effects. And at the end, the activation energy effect is also studied on the flow behaviors. The geometry of the problem is a bidirectional stretching surface. Bidirectional mean in three directions, X, Y, and Z. Here, we see that in X direction, the velocity is U is equal to AX, and in Y direction, velocity is defined V is equal to BY. The fluid motions is produced due to the stretching of this surface. On the basis of the above flow assumptions, we are going to model the problem by using continuity equations defined in equation 1 and momentum equations defined in equation 2 and 3. In equation 2, the momentum equations in along X directions. Here, B0 is the applied magnetic field and H2 is the micropolar parameters. And this beta G, rho P, and C minus C, this is the mixed convection effects. In third equations, this is the velocity equations in Y directions. Fourth and fifth equations are the micropolar fluid equations. These are equations is known as micro rotations equations in X and Y directions. Equation number 6 is for temperature equations. Here, the thermal radiation effect is taken, Brownian diffusivity dB, and thermophoresis diffusivity effect dt is also studied. The concentration equation is defined in equation number 7, where similarly dB and dt are the Brownian and diffusion effects, but Kr is the chemical reactions and EA is the activation energy effects. So related to these equations, the boundary conditions are defined in equation number 8. In equation number 9, similarity variables related to the present problem are defined, and by using these similarity variables, the above mentioned partial differential equations are converted into ordinary differential equations, which is defined in equation number 10, which is the temperature velocity equations in dimensionless form in x directions. In equation number 11, the velocity equations in dimensionless form in y direction. Similarly, in equation number 12 and equation number 13 are the micro rotations equations in dimensionless form are defined. In equation number 14, the temperature equation in dimensionless form is defined, where RD is the radiation parameter, PR is the Prandtl number, NB, Brownian motions, and T, thermophrasis parameters. In equation number 15, the concentration equation of the present problems after applying the similarity transformations in dimensionless form is defined. So, by using the above mentioned similarity transformations, the boundary conditions also changed into a dimensionless form, which is defined in equation number 16. After the whole simulations, when we apply a similarity variables and the partial differential equations is converted into ordinary differential equation into a dimensionless form, we obtain some dimensionless parameters such as K is a material parameter, WE is a Williamson fluid parameters, M is the magnetic field parameters, NR is the Bouncy ratio parameters, and mixed convection factor is alpha, the radiation parameter is RD, where sigma is the stretching parameter and PR is the Prandtl number. These are the dimensionless parameter. Similarly, the NB is the Brownian motion parameter, and NT is thermophrasis, SC is Schmide's number, and A is the chemical reaction parameter, and E is the activation energy in dimensionless form, and delta is the temperature difference parameter. These are some dimensionless parameter when we convert the part PDs into ODs. Now, some physical quantities of interest for the present problem are explained in equation number 17 and 18. In equation 17 and 18, the skin friction coefficient in X and Y direction is defined. In equation 19, the Nusselt number, which is used for computation of heat transfer is not transfer. The Chauvet number is defined in equation number 20. Now, when we simulate, convert partial differential equations into ordinary differential equations, then we are going to simulate the problem by using a homotopy analysis methods. The homotopy analysis method is implied for the solution of the present problem. For this investigation, computer-based programming softwares in Mathematica 1012 is used. Now I invite Mr. Muhammad Arif for the result and discussion sections. Thank you. Stops.
Thank you, Mr. Ramzan. Hello, everyone. Very good afternoon to everyone. I'm Muhammad Arif, and I will discuss result and discussion of the current research. Before starting result and discussion, I would like to summarize the whole research, that what we considered in this present research. So the very first is, as Mr. Muhammad Ramzan explained very briefly, I just want to highlight it. We considered three-dimensional MHD flow, Williamson, and micropolar fluids. We also considered the impact of activation energy and thermal radiation impact on the fluid and velocity profile. Similarly, significance of chemical reaction and Brownian motion and thermophoresis and are also considered in the present research. The present flow is developed in the form of highly nonlinear partial differential equations, and we use some appropriate similarity transformation variable in order to transform the partial differential equation into ordinary differential equations. And then the main reason and the main we can say the main reason for highlighting the result and discussion is to explain the impact of various physical parameters physically through various graphs, and phenomena can be highlighted very easily by plotting their graphs. So for graphing, we use the Mathematica software, and for this simulation, we use homotopy analysis technique. So the very first is table 2, which shows the comparison of the present work with the previously published result. So the scan fraction and Nusselt number is compared with Wang result, which is published in 1984, and we check different values of stretching parameter, which is 0. The first one is 0, and you can see that our result is quite identical to the already published work, which validate our work. So in this figure, we change the values of stretching parameter, and we see that both the result, the current and the published work result, are quite identical. So normally in numerical techniques, we need to validate our result. So for that, we need to compare our result with the already published work, which is the agreement, or which verify our result when you compare your result with the already published work. The next is figure 2a and 2b here shows the impact of material parameter, which is represented by K, and the magnetic parameter, which is represented by M. Here, the red line shows the primary velocity, and the blue line shows the secondary velocity. As from the geometry, Mr. Ramzan explained briefly that we have the fluid on a stretching sheet. So the sheet is along x and y axis. So the velocity at x direction is primary velocity, and the velocity at y direction is known as secondary velocity. So in case of material parameter, the velocity of the primary and secondary shows an increment. It is due to the fact that these like the stretch, when we stretch the surface, so the material of the fluid, material parameter, enhance the velocity in both the cases, primary and secondary. Figure 2b shows the impact of magnetic parameter on both the velocities. So from the figure, we can see that by increasing this magnetic parameter, the velocity, primary and secondary velocity, shows a decline behavior. It is due to the fact that when we increase this magnetic parameter, it produces some resistive forces within the fluid, and these resistive forces is known as Lorentz forces. And these Lorentz forces are responsible to decline the velocity of the fluid on this stretching sheet. So as a result, the velocity of the fluid decline by increasing the magnetic parameter or the magnetic values. And you can see both the velocity are declined. Figure 3a and 3b shows the impact of Williamson parameter on the primary and secondary velocity, while figure 3b shows the impact of stretching parameter on both velocities. So first, let me discuss figure 3a. From figure 3a, we can see that the Williamson parameter, increasing the values of Williamson parameter, led an enable increase both the velocities of the fluid, primary and secondary velocity. It is due to the fact that by increasing this parameter can cause some resistive forces and can increase the the viscosity of the fluid. As a result, the more viscous the fluid, the velocity will be decreases. So this Williamson parameter can increase the viscosity of the fluid which is flowing on this stretching sheet. So as a result, the velocity decline, and you can see the declination of velocity in figure 3a. And furthermore, both the velocities, primary and secondary velocity are the red one, and secondary velocity are the blue one. Both are decline. In case of stretching parameter, increasing this stretching parameter, the stretching of the sheet. If we increase the stretching of the sheet, the fluid over the stretching sheet will disturb. So this disturbance is occur in the form of primary and secondary velocity. Primary velocity are the velocity which is acting along x-axis, and secondary velocity are the velocity which is on the y direction. So in case of this stretching parameter, the primary velocity decline because initially the fluid was at rest. So once you stretch, when you stretch the sheet, the velocity will decline, primary velocity, and secondary velocity will increase. And you can see this effect from the figure 3b. Next, we have figure 4a and 4b, which is the primary velocity and the impact of radiation parameter on the primary velocity. So radiation of the fluid, you can say by increasing the radiation parameter, the temperature, the primary velocity shows decline, or you can say radiation is responsible to deaccelerate primary velocity. Similarly, buoyancy ratio and max convection alpha shows here the max convection parameter, which is responsible to accelerate fluid velocity. By increasing this max convection parameter, fluid velocity accelerates. Now figure 5a and 5b shows the variation in micro-rotation profile against material and magnetic parameter. So if you here K represents the material parameter and M is the magnetic parameter, and capital F and G shows the micro-rotation parameter. F shows the primary one and G shows the secondary velocity. So in case of material parameter, both the velocities accelerates by increasing the material parameter. In case of magnetic parameter, the primary velocity accelerates while the secondary velocity deaccelerates. And it is due to the fact that by increasing the magnetic parameter, actually magnet move anti-clockwise. So along x-axis it accelerates the fluid velocity, and along y-axis the fluid velocity it deaccelerates. So that's why primary velocity increase and secondary velocity shows a decline behavior as shown in figure 5b. Next we have figure 6a and 6b, variation of temperature and concentration against magnetic field parameter M and Brownian motion parameter NB. So from figure 6a, the both concentration and temperature of the fluid increases because the impact of this magnetic parameter is considered in concentration and temperature profile of the governing equation. That's why it will affect the temperature and concentration of the Williamson and micropolar fluid, which is flowing on the stretching sheet. So increasing this magnetic parameter is responsible here to increase the concentration and temperature of the fluid in figure 6a. From figure 6b, we can see that the Brownian motion is increasing the temperature of the fluid, and at At the same time, it deaccelerates the concentration of the fluid. From the figure, you can see that the positive values of NB 1357 is accelerating the temperature values and deaccelerating the concentration of the fluid. From figures 7a and 7b shows the variation in temperature and concentration against buoyancy ratio and thermophoresis parameter. So now the radiation, which is responsible to accelerate both concentration and temperature of fluid, while in case of the thermophoresis parameter is also increases the concentration and temperature of the fluid, and which is flowing on the the stretching sheet. Figure 8a shows the impact of Prandtl number on the concentration and temperature of the fluid. Increasing the Prandtl number is responsible to deaccelerate or to decrease the temperature profile of the fluid or temperature of the fluid, while increasing the concentration of the fluid. Similarly, the Schmidt number is highlighted on the concentration profile, which is given in figure 8b. And from the figure, increasing this concentration Schmidt parameter is responsible to deaccelerate the concentration of the fluid. And figure 9a shows the variation of temperature and concentration against chemical reaction and Schmidt number. So here figure, from this, increasing the values of A is decreasing the concentration of the fluid. Here the activation energy also responsible to accelerate the concentration of the fluid. This one can help for the, you can say, proposed work, different Newtonian and non-Newtonian fluid models. This is not a proposed work. This is, we can say, future direction or future work. The researchers who are working in this area, they can extend the present research, and by considering different Newtonian and non-Newtonian fluid models, like they can consider Allred-B fluid model, they can consider Kaysen fluid model, they can consider the Maxwell fluid model, and similarly they can take different, they can solve it by using different numerical technique and compare their result with the published results. Furthermore, different base fluid and nanoparticle can be considered for different scientific reasons. Also, researchers can choose the model and different boundary using different boundary conditions and different geometries. Thank you for your concentration. Thank you so much. This was all about our presentation. If you have any question, you can ask.
Thank you for nice presentation, Mr. Arif and Ramzan. Anyone have any question or suggestion for him? That you can open your microphone and you can ask. Samuel, you don't have any question? Okay. If thank you.
Thank you so
Thank you
much
so
for
much.
listening.
Okay, for
Thank you very much.
presentation. Okay, for the next group is the topic is a conjugate radial line algorithm for equilibrium problem over a fixed point set. Adamu and Asuka, if you're ready, you can share your screen and let's start.
Hello? Hello, can you see me? Can you hear me?
Yeah. It's clear.
Yes, clear. Okay. Good afternoon, everyone. My name is Ibrahim Arzuka. Today, we're presenting our lab seminar together with Adam Yusuf Inwa on the title, A Conjugate Gradient-like Algorithm for Equilibrium Problem over fixed point sets. So these are the outlines of our presentation. So as an introduction, we are going to, let's start with this bifunction. That is, we are interested in solving an equilibrium problem. That is, we want to find an X tilde in K, where this K is a non-empty set such that equation 1 holds. And this problem was initially coined by Ottoli in 1992, and it serves as a generalization of several problems in the literature, such as the fixed point problem, convex observation problem, vertical quality problem, and the rest. Now, for the sake of example, this is the example of convex minimization problem that is which is being given by 2. So we can easily convert this as an equilibrium problem as equation 3. That is where this f is a bifunction, and we say that this equation 3 holds if and only if x solve the complement convex minimization problem, then it solve the equilibrium problem. Similarly, also at a fixed point problem, which is being given by 4, we can easily transform it as an equilibrium problem given by 5. And we say that X solves the equilibrium problem if and only if it solves the fixed point problem. Thirdly, this is just an example in Nash equilibrium, which is of non-cooperative game, where this denotes the sets of the strategy of the I player I to n respectively, and this is the hi denotes the payoff function of each player. Then this n tuple is called a Nash equilibrium if this condition holds. So this problem can easily also be formulated as an equilibrium problem as equation 7. So these are some area of application in game theory and in EcoPark, which this one is a well-known problem. That is the prisoner dilemma. So actually, in this presentation, we wanted to solve a problem of this type, a problem of this type, that is K is a subset of the Hilbert space, and this Ti is a family of beta demi-contractive mapping. And F is a bifunction, that is, we want to find an X star in the intersection of the fixed point of this of this mapping. So these are some of the definitions that I'm going to use and some properties of some mapping. And this, we said that let K be a subset of Hilbert space, then the mapping is set to be D demi-contractive if the set of fixed point of T is not empty, and there is this D in this interval such that this inequality holds. Similarly, now if the set of fixed point is not an empty set and this inequality holds, then we say that the mapping is quasi non-expressive mapping. Similarly, it also holds for demi-cross as 0, that if this inequality holds. So these are another thing that we use. We assume that T is demi-contractive mapping such that the fixed point of T is not empty set, and this alpha is in this interval. Then the mapping, this additive mapping, is quasi non-expressive on T such that this inequality holds. And this is just the definition of projection mapping, which is well known in the literature. So this is the characterization of the mapping, and also this definition tree is eta matrix projection of X on H, which is given by this inequality. And these are some property also that we use, and this is the E diagonal subdifferential of the second term of the bifunction. So these are the lemmas that we use in establishing the convergence of the proposed method. That is where This is the Kaskazoo lemma, but it's extended form. So I will give it to my partner.
Afternoon all. I think in 2021, and developed the following algorithm in order to solve the equilibrium problem over the fixed point set, which was the fixed point set. So he used the following algorithm 9, and he make the following assumption on the sequence on the parameters of his own algorithm. So you can see the algorithm has many conditions. It needs Lipschitz continuity on the contractive mappings. We have some, what matter by this, we try to improve this algorithm. So we use a conjugate gradient like we change the direction using a conjugate like for this, and we also relax some of the condition and the parameters, like we get rid of the Lipschitz constant in terms of the mappings TIs, and also that algorithm is self-adaptive. So you see this is the algorithm. So we use this, and these are the conditions that we only require. This conditions are not much as in the previous one. So we have the following lemma. So if the sequence YK is given by the algorithm, then the direction DK is bounded, and that the sequence YK and XK converge to the solution of the problem of the fixed equilibrium problem over a fixed point set. So we have this theorem, and we apply this result to solve a variation inequality problem. So suppose this is a variation inequality problem. Suppose A is a linear mapping, then this is the equivalent version of our problem in terms of variational inequality problem. So it's equation 13. And this is the corresponding algorithm for the variational inequality problem. And we have this is the corresponding theorem convergence result for the variational inequality problem. And now we have the numerical illustration. So what we did, so for this example, we consider R5, and we let K to be the following polyhedral constant complex set, which is given by this. And we define our bifunction f of xy as this, where the function A is given by this, and the matrix Q is given by this, where M and N are N by N matrices. N is Q symmetric, and S is an N by N diagonal matrix, and Q is just a vector in Rn. So with the mapping, these are here we consider only two mappings, TIs. We consider T1 and T2, which are the contractive mappings. So you can see that the function f is easy to see that this is a kappa minus number of Q minus 1 Strong-Gilly monotone. And you can see from the definition of the bifunction that the subdifferential is nothing but AX plus QX plus Q, or at any point into how to compute the subdifferential. So here we perform a numerical test using MATLAB R2 2022 with the other characteristics of the computer we use. And we take the matrices we use our denominator in the interval 0, 3, and with the quadratic program solver, and we take the error of this. And in the first test, we set kappa to be equal to 50 plus number of Q. These are the main parameters we use. And then the results for the algorithm, let me show in figure 1. And then in the second test, we compare our result with the result of AN. And we show the result in figure 2 and 3. So this is the first one result. You see, these are for the coordinate values of the coordinates. You can see that it converges, they all converge to 0, which is the equilibrium point. The point 0, 0, 0, 5 in each coordinate. These are we show we compute error against number of iteration, and here we show error against the number of times it needs to show the convergence. It takes about a second to convert, and here we showed our results compared to the result of AN. You see the blue one is on which converges faster than the result of AND. And here we give another example in infinite dimensional spaces. These are the function. This is the bifunction F, and these are for the mapping CI. We take these projections and this onto the following half space HIs, and here we show the trajectories of for the point different initial points. The first time we consider x initial point as t square plus 1, second one is 1 over t plus 1, and the other is exponential t. These are the trajectories. And this is, and thank you for listening.
Any question? Adamu, I have one question.
Okay.
At the first part, I see the by
What?
in the first part on your introduction, can you move? Yeah, back. Oh, okay, last slide. Next.
This one?
Yeah, next slide.
This one?
Next slide. That I see at the by level, right? Or by function, I'm not sure. This next slide. This
one?
Your problem is the by level, right?
No, it's a simple equilibrium problem.
Oh, only equilibrium problem, right? Not applied to
Yes.
the by level, right?
Yes.
And so by the and apply to variational for solve the
Yeah,
solution, right?
Yes, we use.
Okay. Thank you.
Okay, no
Any
problem.
question
Thank you.
or suggestion, everyone? Okay. Thank you for nice presentation. Okay. For next is the last group. An improved conjugate gradient method for Riemannian manifold on non-convex optimization problem by Nasiru and Sunny. You ready? You can let's start.
Okay.
You have 30 minutes for presentation.
Oh, thank you very much for this wonderful event. Can you hear me clearly?
Yeah, it's clear.
Okay, okay. Actually, I want to make it. Can you see the screen?
Yeah, you can share full screen. But for now, it's not full screen.
Oh, for now, not full. Okay.
Yeah. Control L. You can use.
Control L.
Control L. Yeah.
Okay, thank you for this. Okay. I am Sani Salisu, and my colleague here with me is Nasiru Salihu. And today we will be discussing on an improved conjugate gradient method for Riemannian manifold on non-convex optimization problems. Okay, I will take part on the first part of the presentation, and then my colleague will continue from where I stop. The content will start with the basics of manifold optimization, leading to conjugate gradient from Euclidean to manifold, which comprises of line search CG parameters and repair tools and sufficient descent conditions, which are essential of establishing convergence. And then we discuss on the appropriate procedures of establishing convergence. Starting with optimization schemes, first of all, we will require to have a nice manifold. A nice manifold here, we mean a manifold that is smooth. smooth, then we need to have a smooth function. And once you have a smooth function from that manifold, say M to R, and then you can decide to look for a particular point which optimizes the function. And this is like graphical visualization of the mathematics represented here. You can see this is example of smooth manifold by M, and this is the F, taking a value, taking a point from the manifold and mapping it to R. So this is just to visualize what it is. An essential part of the manifold optimization is the tangent space. So the tangent is something that is very flat. It's like a reflection of what is contained in the manifold, but on a straight line, such that one can discuss about direction and other things. A very nice example of such manifold is what is called Stafford manifold, and it is defined by this relation. Of course, a particular case of this is the spatial orthogonal group. And this spatial orthogonal group is very, very useful in robotic control. As you can see, it has to do with rotation. Once you are into Lie group or Lie theory, you will understand that SON, especially SO3, describe motion on R3. So, and that has to do with both rotation, and then when it is incorporated into SE3, you will have the translation, and then with escalation, yes. And we have many other applications. This is just to mention a few. Remember, the essential fact is having a nice manifold. Then whenever you have a point on that nice manifold, let's say X, then you need to compute, or you need to find a tangent space. That is to say, what is flat on that point. And this is how it is done. For example, this is a point X, and then the flatness here is what is called TXM, which is tangent space at X. Oh, this is interesting, but one needs to be careful here, because if you change the point, then the tangent space may have to change depending on the situation of the manifold. If you are dealing with non-regular shaped manifold, definitely once you change the point, you will have a different tangent space. And this is really crazy, it's not easy to manage, but we'll find a way to show how it is done in the existing results. One can recall from the classical setting of optimization that the regular thing is have a point, for example, then you need to find a certain direction of which you will obtain the optimizer. And that direction is what is termed as Bn. And then to what extent you will scale that direction, which is alpha n. Alpha n is step size, which will have to determine what extent you are going to scale the direction so as to reach an appropriate point, which is close enough to the desired point. And iteratively, you repeat the process. That will give you the optimizer, depending on the function involved. Okay. An example of this method, which is very prominent, is the Newton method. You can see how it is described. This is Newton method, very old method, but one can notice that, of course, this requires a computation of second derivative, and that make it a very expensive in terms of computationally expensive, and also with other challenges depending on the function involved, because sometimes we'll have functions that are not even twice differentiable. That is it. Another appropriate method is what is termed as Stafford descent method, and this is how it is described. But all of these methods are very useful, but one important of Stafford descent is that it only requires first derivative, and then we do not need the function to have twice differentiability. That is very good, especially if you have a complex function, then this can help alongside. Once it is differentiable, you can obtain the minimizer. Oh, you can see the general format remains. You are adding a particular size, which is alpha n, once you relate it with this, and then with certain direction. For Stafford descent, the direction is minus gradient of f, and then we have the alpha n. This really helps in reaching out to the optimizer. General question or challenges associated to the manifold is that, do we do addition as it is in the usual sense? No. Do we have scalar product? No. Do we have direction or gradient. Remember, manifold is not a vector, so we don't have direction. So we have to mimic the idea of direction. And the direction has to be described from the tangent space. Of course, the gradient happens to turn out to be in the tangent space because it's not like the gradient from the classical setting, or this gradient described by the manifold structure. Of course, that helps in obtaining the minimization algorithm or optimization algorithm in general. A very important tool for that is what is termed as retraction. A retraction is nothing but a map, taking an element from the tangent space, getting it back to the manifold. For example, you have a point X, you will have to find a direction at which you will get the next point. But having that direction, remember the direction you will locate it at the tangent space at X. But then that is not on the manifold. You will need to have the updated point on the manifold. Then you will have to apply retraction to get it back to the manifold. And that is retraction, and this is how it is described mathematically. Of course, you can see the geometrical representation here is much more convenient for layman understanding. But however, the mathematical representation is very useful, especially when it comes to the proof. And that is how it's done. A second important tool is what is termed as vector transport. Why do we need vector transport? Okay. If you change from a point to another point, you remember that the tangent space changes. For example, I change from X here to Rx of theta X, then the tangent space changes. But remember, in most cases, one requires information of the previous direction to get the current direction. So how do we do that? They both belong to different tangent spaces. Then we really need to find a way to communicate between the existing two tangent spaces. And that way we require vector transport. That is to transport a certain vector from a particular tangent space into another tangent space. So as to communicate together, you can be able to add them then, or you can be able to subtract between them once it is communicated. And this is how it is defined mathematically. I don't have to go into that because the graphical representation say it all. Okay, this is the general structure now. You have an iterate, let's say x at n. For example, xn here, xn in M, that is for a particular n, you have a point in the manifold. Then you need to locate a tangent direction on the tangent space here. Once you have the direction, then you can update it by this xn plus 1. And this is how it is updated. This is a way to represent the general optimization algorithm, and repeating the process until desired element is achieved. Okay, so this is just to have a visualization of how it is done. This is x naught, for example. This is eta naught, the direction for moving to the next point. Then from that, you have to apply retraction. You apply retraction, then you take it back to the manifold. You can see how it is applied to the manifold. Then you have x1. X1 here, you also need to locate a direction for moving to the next level. And that direction, you apply retraction again, you move to x2. And it goes continuously in that manner. So this is all about the basic idea. And my colleague here would like to continue from the desired tool. Because okay, Sharon? Okay.
Waiting Nasiro, right?
Yes, he's going to share and then.
Okay. Nasiro, can you share your screen? Okay. Okay, I see. But
ai ban ga wancan din bane, ban san ya zan yin gan shi bane ba. Eh? What do you mean? Okay. Then ya zan yin ga desktop ɗin daga nan yanzu. Inda na share. Ba ka buɗe shi ba? Ai gashi nan yana buɗe ba wannan oh gashi nan exactly. Double click. Shi ne ko? Control L. Bari in yi da wannan ɗin kai.
Now?
Okay, now ya buɗe? Ah, to it's okay.
Kawai buɗe shi za ka fi.
Ai na yi control L na ga bai yi bane. Ina yake ne a nan? A nan yake gaskiya, a nan ƙasa yake. Nan ne ko? Nan ne nake gani yawa gashi nan. Okay, good afternoon, everyone. Can you hear me? Okay, in continuation with our group presentation today. Yeah, you moving, yeah. So, okay, I think it's okay now. In continuation with our group presentation, I'm going to continue from where my colleague in person of Sani Salisu stopped. That is CG Euclidean to manifold. First of all, our main goal is to minimize this given function where the search space is in the manifold. That is on the manifold instead of on usual Euclidean spaces. In order to make a jump, that is an extension from Euclidean optimization to Riemannian optimization, we need some basic structures. That is, we require line search to be extended to manifold. So also the search direction and some Riemannian conjugate gradient, that is Euclidean conjugate gradient need to be extended to Riemannian conjugate gradient parameters. In order to show the convergence of the algorithm, we require the search direction to be descent, that is sufficient descent. And we also need to show the global convergence of the algorithms. First of all, we require some basic definitions in order to make this generalization, which one of the first of this definition is inner product, which is given by definition 1. Based on this definition, we have gradients, that is Riemannian gradient, which is defined by this, whereby in second definition, we are going to use the definition, the concept of retraction, which is discussed by the previous speaker. So also we need the concept of vector transport in order to make this generalization. These definitions are taken from Baumol, Introduction to Optimization on Smooth Manifolds. As I said earlier, that given a function f, which takes points from manifold and it outputs it to R. So our aim here is to find the minimizer, that is X star, which is on the manifold that satisfies this given condition. In our usual Euclidean conjugate gradients techniques, that is iterative method, we normally use this technique in order to move from one point to the other. This is a linear in nature, meaning that we have the concept of addition and scalar multiplication in this iterative scheme. So how can we get the replica of this in Riemannian optimization, which is discussed by the previous speaker given by this? In 1994, Smith observed that in order to make this generalization, we require the concept of a parallel exponential map and a parallel transport. But these are computationally expensive because based on that, Absil, Mahoney, and Sepultura in 2008 find a relaxation of these maps, which are represented by retraction and vector transport respectively. So based on that, we can now generalize the line search, which is normally used in order to move around from one point to the other. The force of this line search in Euclidean setting is given by Armijo line search, which ensures that there is a substantial reduction in the value of the objective function at each iteration. Now, that's not enough because we need the value of the step size, that is alpha k, which is given by the step size, not to be too large or too small. So if we want to do that, we need to combine this Armijo line search with the second condition given by this, which is called Cavacho condition. When we combine the two, we have standard Wolf line search in Euclidean setting. In order to make this generalization, that is extend this line search to Riemannian settings, we need definition 1, that is inner products, and definition 2, that is retraction, whereby the concept of linear, that is the addition we have in the linear, in the Euclidean CG setting can be extended down to Riemannian manifold as this, whereby if you combine these two, we have what we call Riemannian standard Wolf line search. Sometimes the convergence structure of a standard Wolf line search may not be encouraging. So we may need a stronger version of that, which is called strong Wolf lines condition. And this condition is given by these two inequalities, whereby its or their generalization is to Riemannian manifold is given by the other two inequalities, which were generalized by Ring and With in 2012 in order to show the convergence of a Riemannian Fleet-Harris conjugate gradient method. We are going to talk later about that in the course of this presentation. Another important component in order to make this generalization, as we talked earlier, is the search direction, which is given by this in Euclidean setting. That is, in Euclidean conjugate gradient method, the search direction is always given by this. Here, the major challenge here is that the index, that is eta k, at k index and k minus 1 index are sitting in different tangent spaces, which is impossible to replace these two in Riemannian setting. So based on that, we need the concept of vector transport. That is, we can now transport the vectors at the tangent space of k to, or k minus 1 to the tangent space of k, given by these, so that we can now represent the classical CG search direction in Euclidean setting to Riemannian given by this structure. And this is also given by Ring and With in 2012 when they are trying to show or extend the conjugate gradient methods, that is Fleet-Harris conjugate gradient method to Riemannian manifold. There are some classical CG parameters in Euclidean settings which we already extended to Riemannian conjugate gradient method. Some of these classical CG settings or parameters are, we have beta k HS, we have beta k PRP, and LS. These three parameters are considered to be numerically effective because of restart strategy. The strategies that allow them, if they are taking a short steps, to restart themselves in order to, as a speed descent method, in order not to continue taking short steps. The other group, which are given by this set of parameters, are considered to have a very good convergence property, but their numerical performance is not always good. So, as I said earlier, that the first CG extension to Riemannian was given by Ring and With in 2012 using this parameter Fleischer Reeves. here in this work, we are going to look at some improved version of beta k dy. That is the extension of beta k dy to Riemannian manifolds. As we talked earlier that beta khs is given by this, when we take yk minus 1, that is the difference between two consecutive gradients, we can now extend this to Riemannian manifold, that is Riemannian CG as this. So also we look at the Fletcher-Reeves. This is straightforward to extend because it has no any vector transport there. The other 4 CG parameters in Euclidean settings are therefore extended to Riemannian CG parameters as follows. So these are some related work on Riemannian CG. As I said earlier, that ring width established the convergence of Fletcher-Reeves with strong Wolf conditions. Later on, Sato in 2015 or 2016 extend the Riemannian dy, that is Euclidean dy to Riemannian, and show that his method generates the descent direction and converge globally using weak Wolf-like side. This one is using the standard Wolf-line set, a strong Wolf-line set, while this is using weak Wolf-line set. That is Riemannian weak Wolf-line set condition. So we want to improve on this work of 8, whereby we want to show the convergence of RDY, that is Riemannian di and Yuan CG parameter without line set consideration. In 2021, Sakai and Iduka used strong Wolf line set in order to show the convergence of PRP and HS matrices respectively, using some kind of a hybrid structure. So recently, Tang in 2023 showed the convergence of RCG method, whereby they extend the concept of spectral, incorporated the concept of spectral into the Riemannian CG structure, whereby they show the convergence and global and sufficient descent of the method, as well as a computational analysis based on this hybrid parameter. Our new conjugate gradient method is motivated by the work of Zhu et al. In 2020, whereby they proposed the following dy parameters with these structures. So we want to see, or we want to extend and generalize these structures into or onto the Riemannian CG parameters based on the definition 1, 2, 3 above. So in order to make this generalization, if you observe here, we have GK transpose DK, which means we need vector transpose here, so also here, so also here, so also here. So many places there we need the concept of vector transpose, which is given by definition 3 here. So applying these definitions, we can now generalize the parameters proposed by Zhu et al. In 2020. That is DDY1 onto Riemannian CG parameter like this. So also the second parameter can be extended to CG parameter in this form. So in order to show the sufficient descent condition, that is to ensure that indeed the direction followed will lead us to minimizer, we require this theorem given by theorem 1, whereby what this theorem is always doing is that it's trying to show us that indeed we are indeed minimizing. So in order to show the convergence of a given Riemannian conjugate algorithm, there is what we call ring width non-expensive condition, which ensures that the norm of the vector transpose does not exceed the norm of the search direction on the tangent space. So based on this inequality, we can now show the convergence of a given algorithm. So also, we require the Lipschitz version of Euclidean conjugate gradient method in Riemannian conjugate setting in order to show the convergence, and the as well Zautendig condition is also required in order to show the convergence. So we will require all these two theorems in order to show the convergence of the algorithm. The last theorem here is saying that irrespective of where we start from, we are definitely going to ensure that the algorithm converges. So this is an ongoing work. So we are still working on the work. In order to implement the algorithm, the setting or the Riemannian CG algorithm is given by this. So these are some Riemannian optimization problem that we will use in order to implement these algorithms. And these are some study materials in order used in compiling these projects. These two are on Euclidean CG parameters or Euclidean CG conjugate gradients in general, while the other two are on Riemannian conjugate gradients in general. So thank you for listening.
Any questions or suggestion? Okay. No?
Please ask
Um,
question.
Yeah. Okay, if no question, thank you for nice presentation, everyone. Please turn on your camera for take a picture. Okay, wait please.